Okay, good morning. Can you hear me? Yes, no? What about now? Okay. So, good morning. Today we conclude the overview of the 6LoWPAN stack, which means that we will have to cover the application layer of 6LoWPAN. Just as the usual wrap up, what we have learned so far is that basically the 6LoWPAN stack is based on the physical and medium access control layer, which are common as the Zigbee's one, which are basically the 802.15.4 physical and medium access control layer. Then 6LoWPAN stack provides adaptation layer which are used to let IP be usable on top of 15.4. And till last time we have overviewed such adaptation features or layers. We have seen that these adaptation features basically are dealing with header compression and fragmentation. We have also mentioned that the 6LoWPAN stack also provides some routing protocol which is specific for 6LoWPAN by itself, which is called Ripple, which we have commented on last time. Okay, so today basically we move up one layer and we start seeing how applications can be actually conveyed on top of 6LoWPAN networks. Okay. So the topic for today is the constraint application protocol. That we will see is the reference protocol design for the application layer of 6LoWPAN. Okay. So basically, as a background, let's say the macro objective of COAP is actually to enable web-like services on top of 6LoWPAN networks. Okay, and by web-like service I mean ways of interaction between application programs or protocols which resemble how application protocols actually interact in the classical internet. Okay, so which resemble somehow the main pattern, the main structure, which is which you can find in the internet at the application layer. Okay, with all the problems which come from the fact that we are dealing with again resource constrained networks and network scenarios. Okay. The point is, as for all the other protocols which we have seen so far, is that this kind of web-based solutions which are out there in the internet, they're not applicable as they are to the environment of low-power networks. Okay, so we actually want to redesign or reshape how these web-based solutions are done, okay, such that they can be compliant to, again, the reference scenario we are talking about, okay? And as we will see, this, outcome, the final result of this redesign is this COAP application layer protocol. COAP stands for Constrained Application Layer Protocol, which is again the reference design for building up applications in 6LoWPAN networks. Okay. So just a very, very short and brief digression on how application services are actually managed in the internet. Okay, so if you think of how these services are managed in the internet, you can see that regardless the specific application you're talking about, okay, you can find in any of these applications some common ingredients. Okay, for example, if you think of what the resource is in the internet, like a web page or a piece of file or whatever, okay, It's true for most of the application services which are offered in the internet that these resources are located at some places, okay, which are called servers. Okay? So if you want to download a web page, you have to go to a Google web server or to a web server. If you want to retrieve a file, you want to go to a FTP kind of server. If you want to download a piece of code through BitTorrent, for example, you have first to locate where the resource is present, okay? And then you have to go there, and this place where the resource is present is kind of a server by itself, okay? So you really want to, in the internet, you really have different places where resources are stored, which are called servers, okay? Then, in most of the application services which are out there in the internet, these resources are uniquely addressable or addressed by some specific names which are called URIs, okay? Which we will discuss a little bit in the following slides, okay? And the third ingredient is how you actually access to these resources, okay? And this way of accessing resources is often synchronous, which means that you need something at some point of time, okay? You issue a request for this something, a web page, a piece of file, and so on and so forth, okay? And the entity which is responsible of having this piece of file or resource answers you synchronously, which means that there is a direct binding between a request and a response, okay? You want a piece of information and you get it just like you requested, okay? In the very same time you have requested, okay? So these kind of ingredients, if you put them together, okay, this has a name, which is called REST, which stands for Representational State Transfer, which is a paradigm to design application service in the internet. I guess that the most of you is already familiar with this kind of concepts. For example, for sure, those of you which are more computer science, which are following computer engineering, okay. Again, that's just a name, REST, under which, the meaning of which is basically explained by these ingredients. Okay, you have resources, they must be identified uniquely through these URIs. Resources are at servers, and the exchange pattern to get these resources is synchronous. Okay, which means that I issue a request and the resource comes back to me straight away without any delay. Okay, synchronous transfer. Okay. Then, if you look at the picture on the right-hand side of the slide, you have some of these components which somehow belong to this REST state transfer mode, okay, or the main components, let's say. We have already spoken of the servers, which are where the resources are, okay. The clients is basically the part of the application service which usually issues requests for resources. So basically, it's your web browser, your FTP client, and so on and so forth. Okay. And the third component, which we have not yet discussed about, is the so-called proxy, okay, which you can think of as an application layer router. So it's some kind of relaying device which operates at the application layer, okay, which may intercept, for example, requests coming from clients here, okay, and then redirect the request properly through towards a specific server. Okay, so these are, let's say, the main three ingredients of REST kind of transfer, and these are the main architectural components which you happen to find in this kind of REST transfer mode. Okay, is it clear? Anything not so clear? Okay. So this is where we are in the internet. Or let's say where most of the application, or how most of the applications are actually designed and shaped in the classical internet. Okay. Just one quick slide on the URIs. Okay. What we are interested in here is basically the so-called URL. URL is a standard way of addressing resources in the internet. I mean, giving names to application layer resources in the internet. Okay. And what we are interested in most is the so-called URL, okay, which is basically the name which you use to, again, specify where the resource is and what the resource is in this REST kind of transfer mode. Okay? So if you look at this URL scheme, you have the first part of the scheme, that's a string, okay, it's a character string, okay? You have the first part of this URL, which is telling you what kind of scheme, what kind of protocol you are actually using to get the resource down from where it is, from the server, okay? So for example, if you're using HTTP, you will see listed here HTTP, okay? Then you have something which is called authority or main site, okay, which is basically telling you what's the name of the server where the resource is, okay? In this case, the name is www.example.org, okay? Symbolic name. And then you have a bunch of characters which follow the authority name, which are used to specify different things. The first one is what kind of port you're using to access the specific resource on a specific server, okay? And then what follows is basically the path to that resource. Okay, so where the resource is located at that specific server. For example, in this case, this means that the resource I'm interested in is on this server. You can access it through this port 8080, okay? And the path to get the resource is sensors, and then you can also specify something which is called query or query specifier and so on and so forth, which is basically an indication on what you really want to know about that specific resource. Okay? Clear? Example. In this case, I want to access a resource which is called sensors, okay, on that specific server, and I want to query this resource to get the light, to get out the lumen kind of information about the specific resource I'm querying. Okay? Clear? So keep this in mind because it will be useful when talking about COAP. Okay? In COAP, we have a very similar way of addressing resources. Actually, it's the same way of addressing resources with some modification. Okay, one of which is basically that we don't have here any longer the HTTP acronym, but we have something different, which is COAP, for example. Okay, but the format of how we want to address resources, okay, it's more or less the same as the one specified by the URL. Okay. Okay, so again, we are still in the classical internet. So we are still in the world we know best. Okay. Let's see how we can actually get practically one specific resource by using one of the main application layer protocols which are out there in the internet, which is the HTTP. Okay. Who has not studied HTTP before? Who has not studied? Who does not know what HTTP is? HTTP. No one. So everybody knows at least what HTTP is and how it works, right? Okay. So suppose that we want to take HTTP and port HTTP into a sensor network. Okay? And suppose that we want to use HTTP to get out information, out a sensor node. Okay? For example, suppose that we want to use HTTP to get a temperature sample out of a sensor node. Okay? First question. We have said that HTTP uses a REST kind of paradigm, which means that we have to identify who is the server, where is the server, and who is the client, and where is the client. Okay? So in this very case, which means reference application is get out temperature sample out of a sensor network or a sensor node. Okay? What is the server and what is the client? If you want to use HTTP to get out this information, So where would you place the server side and where would you place the client side? If you had to use a REST kind of HTTP-like paradigm to get out the temperature sample out of a sensor node. Who is the server and who is the client? So the client is commonly who is asking, who is issuing the resource request. Okay, so he's interested. The guy who is interested in knowing, in this case, the temperature sample. Okay, which is, for example, anyone. Okay, which can be myself or any one of you. Okay, and the server is in the REST paradigm the entity which is providing the resource. In this case, the resource is a temperature sample, which means that we have to place the server on the sensor node. Okay, and this is one of the main criticalities which we have to face if you had to port web-like REST paradigm onto sensor networks, because the server has to be placed on sensor nodes, so on constrained devices. Okay. Suppose we can do it. So suppose we can actually run a server, an HTTP server on a sensor node. Okay. If we are able to do that, we can then use HTTP, plain HTTP, to get out the temperature sample out of the sensor node. Okay. And how would you do it? So you have basically this guy here. Up here is the sensor node who is running this HTTP server and has some local resources like temperature and others. And there is someone else in the network which runs a client. It can be a node in the network itself, or it can be someone which is outside the sensor network. Okay. Whenever this guy has to get a temperature sample from this server, it has basically to undergo all the procedures which are specific for the HTTP. So, for example, it can issue a GET message, which is an HTTP GET message, requesting the specific resource, which is /temperature in this case. And then this server, which has this resource, will then answer through a kind of HTTP response message, which, as you should know, includes a status code, which tells you whether the request is acceptable or not. And then, if the request is acceptable, it includes also the resource which was requested. So, for example, in this case, the transaction is get me a temperature sample, and the response is fine, 200 OK, it means I've correctly answered to this request. And then the body of this response message includes the temperature sample. Okay, clear? So, if you want to implement this kind of scheme using HTTP on sensor node, okay, most likely the transport layer, which has to transfer both the requests from the client to the server and the responses from the server to the client, are to be transferred through TCP. Okay, which means that if we look one layer down with respect to the application layer, always in the same application example of temperature samples, what happens from the transport side is that basically the client side, the one who is willing to get this temperature sample, has to establish a TCP connection to the server side with the procedures which we have studied in other courses. And then, only when this TCP connection is out there, is running, I would say, it can actually issue an HTTP GET request. So whenever a TCP connection is active, we can actually move on by conveying HTTP messages through TCP connections. Okay? And then what you have is basically, after you got the resource, you may want, for example, to terminate the TCP connection, to tear down the TCP connection. Okay? Clear? So this is basically what you would do if you had to implement HTTP in sensor nodes, sensor networks. Okay. What kind of problems you have? Why don't you do it? For the very same reason as in most of the other cases, because this kind of transaction, okay, has a lot of overhead, and the overhead you can see clearly here is basically both in the transport layer. We don't really want to use TCP. This is something we made clear also last times, right? Because TCP is very heavy, because it actually creates a connection-oriented channel at the transport layer between client and server, which you don't want to have because you have duty cycling in sensor networks, which means that some sensor may be out, may be running or not depending on time. Okay. And then it's heavy in terms of segment headers. So the what do you call it? The signal information which must be conveyed for every TCP segment which is sent out. Okay. And then also, if you focus on the HTTP kind of part, so assuming that TCP is out of the picture, if you only focus on HTTP, still also the HTTP protocol is too heavy because it has again a header and overhead which it's not negligible, okay, because it has a lot of methods, meaning a lot of ways you can request or you can put information onto servers, okay, and third reason is because it's synchronous, which means that whenever someone issues a request, it needs to have a response straight away, okay? Which again might not be the case in sensor networks because, for example, the server may be sleeping at some time, okay? So this synchronous kind of state REST transfer is not good for our specific case, okay? Clear? Questions? Okay. So let's see what this COAP is, though. And as usual, let's start from the architectural description of COAP. So what are the elements which belong to the COAP environment? Basically, it's the same kind of devices or entities which you find in classical HTTP-like connectivity, in the sense that you still have servers, you still have clients, and you still have proxies. Okay. What it changes is basically how this interaction between these entities is managed. Okay. So in sensor networks, this interaction better. In 6LoWPAN, networks, interaction is managed through COAP. Okay. So basically, clients and servers speak COAP. Within the sensor network. They may speak COAP also between sensor network and the internet, which means that there might be some servers in the internet which are COAP enabled, which know basically the COAP semantics and grammar, so they can actually speak COAP with sensor node directly. And then in this architectural description, we also have some proxies, okay, in the middle, which are able to translate, for example, HTTP into COAP and vice versa. Okay, because we really want, for example, to access a sensor node from this PC by using the protocols which are PC specific. So I really want to read a temperature sample on a sensor node, for example, by using HTTP from my PC. Which means that in between my PC and the sensor node which I'm reading, there must be someone which translates my HTTP requests into COAP requests and does the other way around to read the responses. Okay? And this someone is a proxy. Clear? So, one functional distinction between the proxy you see here and the proxy you have seen in the previous slide, in the classical, let's say, HTTP architecture, is that this proxy here performs protocol translation, which means that it takes COAP from this side and then translates it into HTTP and vice versa. Okay? The proxy we have seen in the previous slide was an HTTP proxy plain, which was just behaving as an intermediary between two HTTP entities. Okay, clear? Questions? Okay, so this is a kind of messy picture. The most important message which you should get from this picture is this stack here, okay, which is the reference stack, the stack on the left-hand side of the picture, which is the reference stack for 6LoWPAN or COAP-enabled 6LoWPANs. Why is it important? Because, as you can see, COAP is the only application layer protocol specified, standardized for 6LoWPAN networks. Okay, there's nothing else, at least non-standard. Okay, and the second message is that you don't have TCP, which means that the only transport layer protocol which you have is the UDP one. Okay. Why these are two important, let's say, observation? The first one is important because it means that since COAP is the only one with the application layer, it must be able to do most of the things which in the classical internet are done with multiple protocols, like FTP, HTTP, SMTP, and so on and so forth. Okay? So in a sense, COAP is a more general protocol than classical HTTP. Second information is UDP only. Okay. Why is it? I mean, why it's something you should take care of? Why it's something you should be aware of having UDP here? So what's the impact of having UDP here? I mean, the advantage is clear, right? It's much more lightweight than TCP. So it's less heavy than TCP, right? What's the drawback of having UDP here? So what should you be aware of?
There's no connection.
There's no connection, and so what else? So, which are the features which TCP has and UDP does not have? Connection oriented is one of these features. What else? Huh? Okay, so TCP is a reliable protocol, which means that whatever is transmitted has 100% probability to be received. Okay? If something goes wrong, TCP takes care of it by retransmission and so on and so forth. Okay? What else? Okay, so TCP implements congestion control, flow control, and so on and so forth, which means that TCP adapts transmission rate on specific conditions of the network and of the sender. Okay? All these features you don't have here, which means that the transmission in low-PAN network, or the transmission of COAP messages in this case, is unreliable, at least at the transport layer, which means it's a kind of best effort service. If it arrives, I'm lucky. Okay, otherwise, no one, at least at this point, does anything to recover from errors. Okay, and then you don't have any, let's say, rate/congestion control mechanism at the transport layer, which means that the only way you have to control the rate which flows in the network is by, let's say, shaping the traffic at the application layer. Okay, because no one does anything at the transport layer to control the rate. Okay, clear? Okay, so let's keep these two features in mind and let's see how these COAP cope with these features. So this is kind of very short abstract of the main features of COAP. Let me just first comment on all of these and then we will see in detail all of these features with some examples, okay? Okay, the first feature is that the URIs of COAP resources is specified, that's very stupid and obvious, by the COAP acronym. So if you want to get access to one resource which is running on a COAP server, you have to specify your requests through this COAP kind of notation. Okay. Second information is it's asynchronous. That's one of the first and main difference with respect to HTTP or plain REST kind of transfer. Okay, asynchronous means here that the response to a request, okay, may not get synchronously. Okay, which means that I issue a request for a specific resource. Okay, the response may arrive delayed in time. Okay, and why is so? Because, for example, the sensor node who is hosting this resource may be busy and doing something else. It may be sleeping or so on and so forth. Okay, but still, I have an ongoing transaction between a client and a server. Okay. So, first important difference with respect to HTTP, this is, or plain REST. Plain REST is synchronous, okay, because all the client and servers are always active and always running at full power, I would like to say. In this case, I may have cases where responses come delayed in time, okay? And again, this is something I have to handle at the protocol level, so at the COAP level, as we will see in a few minutes. Then, as we were saying, this is based on UDP, so COAP is based on UDP, okay? This is something we have already discussed about. And then, what can we do with COAP? So what kind of transactions can we actually implement with COAP? So with respect to HTTP, COAP only takes 4 methods of HTTP. HTTP methods are types of requests or types of messages, let's say. Okay. And these are the 4 methods which are taken up by COAP from HTTP. Okay. The get one is the one we have seen in the example, which is used to ask for specific resources. The following 2, post and put, are used to do the other way around, so to place resources to let's say transfer information from the client side to the server side and not vice versa. Okay. And delete is a method which is used to play with the file server on the server side. For example, for deleting one specific resource on the server side. Okay. HTTP has many more methods than these 4. Okay. COAP is taking up only these 4. Then we are still using URIs. So our resources in COAP must be specified in the very same way or in a similar way we have seen before. So each one resource must have a unique URI, okay, uniform resource indicator or locator. And then there is a bunch of specific features which we will see in the next slides. So COAP has 4-byte header for each message, or better. The shortest header you have is 4 bytes, okay? And then it has a bunch of additional features which specify what is the content, or how the content of each request and response message is to be formatted, okay? And this is something we'll see later on. Last line here is something kind of important because we'll see it next. Okay, just keep this in mind. Okay, so that COAP has these 2 optional transaction modes or behavioral modes, which are called observation and block transfer, because they will be, or they actually are very useful in practical kind of scenarios. Okay. So, if you want to simplify it as much as we can say that COAP is actually taking HTTP as a reference design, pruning some of the things which are not useful in HTTP, like a bunch of additional methods which are not listed here, okay, squeezing in or reducing the header size, okay, and taking the very same REST transfer approach or paradigm, okay, with the only exception that everything can be also asynchronous. Okay, so that's a very, very rough and not accurate summary of what COAP is. So let's see how transaction happens. So how message exchange happens. Okay. So COAP actually is based on UDP. This is something you already know. And the main, let's say, building block of COAP transaction is a message, which is equivalent to HTTP message. Okay. These messages, they all have 4 bytes header, which, as they use, we will see in the next slides. Okay. I mean, they always have the same use to better specify the signaling between client and server in this case. And the first difference with respect to HTTP is that COAP specifies 2 different types of messages. Okay? The first type of messages are called confirmable messages, okay? And the other types of messages are non-confirmable ones. What's the difference? The difference is that if a message is confirmable, okay, who is receiving the message is forced to acknowledge the reception of the message itself. Okay? Which means that if I'm issuing a request for a specific resource using a confirmable message, the server side, which is receiving this confirmable message, has to acknowledge that it has correctly received this message. Okay? This is something which does not exist in HTTP. And why not? Because HTTP relies on TCP. So we don't really need to have confirmable messages at the HTTP level because we are already sure that the message arrived at destination because they rely on top of TCP. Okay? So since COAP is relying on UDP, we need to bring up into the application layer the error control kind of procedure. Okay? By using these confirmable messages. Okay? We'll see what happens when a confirmable message is not acknowledged in a given amount of time. Okay? To anticipate, COAP uses a very simple stop and wait kind of a transmission procedure. So if a confirmable message does not arrive within if a confirmable message is not acknowledged in a given amount of time, okay, then a stop and wait kind of procedure is put in place, which means that the transmitter reissues the same message and so on and so forth. Okay? The other type of messages are non-confirmable ones, which are basically the opposite than confirmable ones, which means that you don't need to acknowledge a non-confirmable message. Okay? Which one to use, it depends on the application. So it depends on what kind of information is traveling in, what kind of resources you are actually requesting. Okay? Then each one message has a unique ID, which is used to, let's say, keep the binding between, for example, acknowledges of confirmable messages and confirmable messages which are acknowledged. Okay? Clear? Questions? So another main difference with respect to HTTP is that this confirmable message kind of definition. Okay? We don't have anything like that in HTTP, so we don't have any error control and error recovery procedure put in place in HTTP. We do have it here because COAP is based on unreliable UDP. Okay? Questions? So that's a typical message exchange pattern in COAP. You have a client side, you have a server side. The left-hand side of the picture shows you an exchange of confirmable messages. The right-hand side is non-confirmable one. The only difference is that basically in non-confirmable transactions, you don't have any acknowledgement. Okay, which means that in non-confirmable transaction, the client just issues or sends a message, and then that's it, in the sense that the server may receive the message or not. Okay? On the other way around, in confirmable message exchange, you have an acknowledgement which comes back after the server has received the message. The binding between what confirmable message is to be acknowledged is maintained by using the IDs which are included in the header part of each message. So each message contains an ID, which is this number here. Okay. which in confirmable kind of transactions must be replicated in the acknowledgement, such that client side can get to know what kind of message is being acknowledged. Okay? Questions? Okay, so this is basically it for messages, which are again the main container of information for COAP. Okay. What about the semantics of this information? So these messages, which are again building blocks, transfer building blocks, can contain both requests and responses. Okay. So if you look at the protocol stack and you kind of explode the COAP level, okay, we can say that the COAP level is composed of two sub-protocols, let's say. The first one, which is the one which deals with messages, confirmable and non-confirmable, okay, and an upper layer protocol which deals with the semantics of these messages, so which deals with the meaning of these messages, okay, which defines basically two types of meanings which a message can have, which is either request or response. So in one, for example, confirmable message, we may find a request, kind of sub-message, or a response kind of sub-message. Okay? Clear? And then these two stuff then are layered on top of UDP. Okay? So request and response are piggybacked, are included somehow in one COAP message. Obviously, then we have to identify what is the content of one COAP message, and this is done by using specific IDs or fields in the header of the message itself. Okay. So let's see some examples. Let's look at the transaction on the left-hand side. Okay, and let's see what happens in the transaction on the left-hand side. Again, I have a client, I have a server. Suppose that the client is always interested in this kind of temperature resource at the server. And to get this temperature resource, it issues a confirmable message, okay, which contains a request message, which is a get/temperature message. Okay. The confirmable message has an ID, which is the one used for the acknowledgement purposes. And also the request message by itself contains a token, okay, which is the name given to the ID to the specific request message, okay, which is in this case 0 times 71. So this confirmable message gets to the server, okay, and here we have many cases. The cases in the picture is the one where the server acknowledges the confirmable message straight away, and then also piggybacks the response to the request in the same acknowledgement, okay? Which is basically saying that the server then generates an acknowledgement message which acknowledges the ID of the message which was sent out, and this message contains the response, which is basically the status code 205. This is the equivalent of the status code of the HTTP, like 200OK, okay, with the content of the temperature sample, okay, and in the response message you have the same token as in the request. So basically, the outside IDs are used to match messages, messages and acknowledgement. The tokens, which are the IDs of the request response, are used to match requests with responses. Okay, clear? So this is the case where basically resource was found. Okay. This is at the right-hand side is the case where the resource is not found. Okay, so you have the same transaction as before. So you have the client which issues a confirmable message, okay, including a request sub-message, let's say, with a specific token and ID. The server in this case does not have the resource, so it still acknowledges the confirmable message, because that's the contract, let's say that's by default. But in the response field, or in the response sub-message, okay, it says I don't have the resource. Okay? And still the token matches the token of the request, the kind of sub-message. Okay? Clear?
Why do you need both the message ID and the token?
That's a very good question. So he's asking, why do you need both the message ID and the token? You need both because, I guess we have a slide on that. Anyways, you need both because one response to one specific request may come in a different message than the acknowledgement one. Okay, let's see if we have a, yes, separate response, here it is. So we prepared it, right? So this is the case where I do the same stuff as before. So I have the client which issues a confirmable message for a specific resource and specifying a specific token for that specific request. Okay? Then the server gets this message, but suppose that it does not have that specific resource ready for some reason. Okay? Still, since the message is confirmable, okay, it has to answer back with an acknowledgement message, which contains basically nothing as let's say a sub-message. Okay? This acknowledgement message matches the confirmable message ID. Okay? When the resource gets available, so when the server side has available these resources which were requested, okay, it issues a new message, which is a confirmable message, or non-confirmable one is the same, specifying the content of the resource which was requested back here. Okay? And as you can see, you have a matching here between the token, which is specified in this message here, with respect to the original. Okay? That's why you need both IDs. Because one is just used to confirm or not messages, or to match or not messages. The other one is used to match request and response transaction, which may not happen in the same message acknowledgement transaction. Okay? Clear? So idea is very simple. Any confirmable message must be acknowledged straight away. Okay? But one specific request may be responded delayed in time. Because, for example, the resource is not available. If this happens, I need to have two IDs to match messages, which must be confirmed, and request responses, which may be delayed in time. Okay? Yes?
Why should server send back? Because the client is starting the transaction. So if the server doesn't get the message,
Where?
the previous one.
Here?
No, previous.
Previous slide?
The server doesn't get the message, so
Here?
why should server send back?
Because this acknowledgement is for having received the previous message, regardless that the server has or not the resource. So it's just for saying, I've received your message.
If
Okay?
the server doesn't receive the message, the transaction will not continue. I mean,
If
should the client send another act to server to say that I have received the last message?
Say again?
The client shouldn't send act to server to say that I have received your message.
In which case? In this case?
Yes.
Here?
Yes. After
No.
receiving the
No. Because what is interesting in this case is that it's a kind of pull-like procedure. So the client is willing to pull something out of the server. So whenever the client has received this piece of information, there's no use to let know the server that it has received the information you want. Okay? That's what happens also in HTTP. So you really need to pull information out of a server. Okay. Other questions? And I mean, this kind of double ID or double addressing, okay, is basically needed because we allow to have responses which are not synchronous. So if all the responses are to be synchronous, you don't really need to have double IDs because you just need the IDs, the addresses of the messages, for example. Okay, but since we are allowing responses to happen delayed in time, you need to keep track to which response, which response is associated to which request. Okay, and then this means that you really need to have double IDs, one for request and responses and one for the messages themselves. You can do the same stuff, so you can implement the same transaction by using non-confirmable messages. Okay, so you can convey the same request into a non-confirmable message, which will have its own ID. Okay. What is the difference here is that you don't need to have, there's no acknowledgement running from server to the client to acknowledge the proper reception of this non-confirmable message. Okay. So as you can see, the server in this case answers to the response to the client with another non-confirmable message, for example, which has an ID which has nothing to do with respect to the previous one, including a response sub-message which don't matches the token which is specified, or the ID which is specified in the associated request. Okay, clear? Again, which one to use? It's up to the designer. It's up to the application designer. Okay, for example, if this is something which happens frequently, so it's kind of a periodic probing one every second for a temperature sample, okay, you don't really need to have acknowledgement for every single request you are issuing, okay, because even if you lose one temperature sample, you have another 1 second in the future, okay. On the other way around, if this is something which is more, let's say, sensitive to reliability. So, for example, this is a measure of some sensor which is posed in a car, which is measuring the stress of a given machinery. Okay. Then, in that case, I really want to have the information, which means that I may use a confirmable message. Okay. But the COAP, in principle, gives you full flexibility on binding confirmable message with request and response, or non-confirmable message with request and responses. Okay? Questions? Okay, so this is the message header of COAP. We will not go, we will actually, I'm just showing it, okay, and then passing away. Just to point out some of the contents which we have seen before. You must have a field in the message which is telling you whether the message is confirmable or not, because this is the field, which is the T field, which is used by the receiver of the message to decide whether to issue an ACK or not. Okay. Then you have the message ID, which is basically that field which is used to match messages with acknowledgements. Okay. And then you have basically all the other fields which you have seen. So you have the code of the message which you're using, request, response, and you have the token in case the message contains a tokenized kind of request-response transaction. Okay. Again, not interested that you remember all the fields in this header. Okay. As any protocol, I would say also COAP has some options. Okay. Again, we will skip these and we will just see in the very end of today 2 examples of options which are actually not so optional, in the sense that they are used quite often in practice. So we'll focus on those. Let's for 1 second get back to the confirmable message transaction. And let's see how COAP enforces reliability. Reliability means that I really want a confirmable message to be received, and I really want the sender of the confirmable message to know when the confirmable message is being received. Okay. This is basically what in the literature is known as ARQ, which stands for Automatic Repeat Request Protocols, which you have studied in other courses like I don't know, networking fundamentals or others, right? And the idea is basically to, I mean, all these kind of ARQs protocol have two ingredients. The first one is a numbering, so I really want to number all the information which is transferred, okay? And the second one is some kind of acknowledgement, so some kind of feedback channel or feedback message which is used to signal whether the message itself was correctly received or not, okay? So COAP uses the most basic ARQ scheme which is available out there, which is the so-called stop and wait. Who has not seen stop and wait so far? So everybody knows what stop and wait is, right? So that's very easy. Stop and wait means that I transfer one message per time, and I want to have each one message I'm transferring acknowledged because I can reissue another message transmission. Okay? If the acknowledgement of any message I'm sending out does not come back within a timeout, which means within a given amount of time, then the sender reads this missing acknowledgement as an error on the channel, which means that it reissues the very same message which he did before. Okay? So in the COAP kind of jargon, what happens is the following. I have a COAP client and a COAP server. Okay? Suppose that the COAP client issues a confirmable message, which includes, in this case, a request for a specific resource. And the resource I'm requesting in this case is kind of humidity. That's just a name. Okay? So the client issues this message. It's a confirmable one, which means that the message carries an ID, which is 0 times 1A. Okay. And then for some reason, the server side does not answer, so does not respond to this confirmable message. Always remember that any confirmable message must be acknowledged straight away, even if the resource which is requested in the confirmable message is not available. Okay? So here I'm missing the acknowledgement because this message got lost somewhere in the network. Always remember that in the middle here you have the network. So you have a bunch of hops, you have Ripple, routing protocol running, and so on and so forth. So all crazy things can happen in the network, which means that packet can get lost. Okay. Packet gets lost, so this guy did not get the acknowledgement, which was due by contract, which means that it waits some timeout value, okay, and then reissues it. So it's a kind of repetitive scheme for getting the acknowledgement back. Okay. All this scheme goes on until the client side gets the acknowledgement of the message it was sending out. Okay, or something happens, which is this another packet, but that's not important for us right now. Okay. This is the same message, which means that it contains the very same message ID, because it's the very same message which needs to be acknowledged by the server side. Okay, clear? Questions? There's obviously, just like in any stop and wait kind of protocol, or in any retransmission-based protocol, an upper limit to the number of times the message can be transmitted or is transmitted consecutively. Okay. If that threshold is exceeded, then the client side just quits sending messages. That's kind of obvious. These are the details. Which is basically telling you how long the client side has to wait for an acknowledgement. Okay. And then what to do in case the acknowledgement does not come back. That's a very kind of sensitive design questions because how long to set a timeout here, so how long to set waiting time for the sender depends on the network. So it depends on where is the sender, where is the receiver, what is in the middle, whether the receiver is sleeping, and so on and so forth. So it's not a kind of trivial question to be answered. Okay. COAP just provides some deadlines, which are basically to choose randomly this number, okay, within a window which is between 2 and 3 seconds. Okay, so I send a confirmable message and I wait for a time which is uniformly distributed between 2 and 3 seconds. Okay, these numbers are heuristically chosen by, for example, making some assumptions on the network size and on the duty cycling of the nodes. Okay. Then what happens when the timeout expires? So if I don't receive the acknowledgement for that specific, after that specific amount of time, as I was saying, I retransmit the packet, the message, sorry, and then I increase the transmission counter, which is the one telling me how many times I have failed so far. And then what I do is also to double the timeout value. So the next time I will not choose, for example, 2.5 seconds as a waiting time, but I will choose 5 seconds. Then I will choose 10 seconds, and so on and so forth. So this basically window size is like increasing exponentially every time you fail, meaning you don't receive the acknowledgement for a specific packet. Okay? As I was saying, this procedure goes on until I receive the acknowledgement or until I receive a reset message from the server, which is telling me basically I cannot handle it. Okay, which means that just quit transmitting or such. Okay? Clear? Questions? Okay. About proxy. So if you remember, in one of the first pictures of this presentation here, we mentioned about proxies enabled to do protocol translation, which means that COAP specifies or allows to have in the architectural overview of the protocol itself some entities which are able to speak HTTP and COAP at the same time. Okay, and the use is the one you were mentioning before. So to let a client running in the classical internet access one resource which is sitting in the 6LoWPAN network, which is exactly what happens in the slide you see here. So you have a client which is at the right here, which is an HTTP client. For example, is my browser. Okay, and through my browser, I want to access a temperature sample or a light sample of a sensor which is running somewhere in the 6LoWPAN network. Okay, I don't want to install COAP in my browser. I want to use HTTP. So I want to use the plugin, the built-in plugin of my browser. By the way, at least the two browsers, which I know, which are Chrome and Firefox, do have COAP plugin, so they can actually also speak COAP. Okay. So I just issue a request using the URI of the resource, which I have to know to get access to one specific sensor node. This is a classical HTTP GET request. Okay. Then this request is routed to a device, to an entity which is a proxy, okay, which is somehow sitting at the boundary of the internet and the 6LoWPAN where the sensor node is. This guy here has the responsibility to translate this HTTP request into a COAP request, so into something which is readable by the server, so by the sensor node. Okay? For example, it translates this HTTP request, which is into a TCP segment, which is into, I don't know, an IP packet. Okay? It translates it into a confirmable COAP message, which includes a request submessage of type gate/light. Okay. Then this message goes to the COAP server, which is the sensor node, okay, which by contract, it answers, since it's a confirmable message, it answers with an acknowledgement message. Okay. Just this message here, specifying the content, which is basically sent back. Then this acknowledgement message, which contains the response to a specific request, gets back the proxy, and the proxy does the other way around. So basically, it takes this response message, which is a COAP one, and translates into a proper HTTP message, okay, which is, for example, 200OK, fine, the source you have requested is available, and the content is such. Okay. What a proxy can also do, so what the COAP specification allows a proxy to do, is also caching, which means that the proxy itself, which receives the response message from some server which are in the 6LoWPAN network, may decide to cache locally that specific resource, just like in web pages, just like any other resource in the internet. Okay? Such that, for example, upcoming requests from the same client or other clients for the same resource, okay, they can be somehow shortcut, okay, at the proxy only, without going to the server in the 6LoWPAN network. Okay, clear? So basically, this is a proper or a classical proxy. Again, with the only difference that it also handles protocol translation. So it does routing at the application layer, it does protocol translation, and it does caching. Okay, routing and caching are two proper functionalities of any proxy. Protocol translation is not, at least on classical HTTP proxies. Okay, clear? Questions? Okay, so let's now have a look at a couple of options, so optional behaviors of COAP, which are actually very useful in practice. The first one is called COAP observation. Again, this is optional, so it's not the usual way of using COAP, but still it's very useful. And this kind of option was introduced because COAP has some shortcomings. The first one and main one being that if you think of the transaction paradigms we have spoken of so far, this is kind of only pull transaction paradigms, which means that there is a client which wants to pull information down from a server. Okay, the server is a sensor node in our case, and the client is somewhere which is interested in some resources available at the sensor node. Okay, clear? That's fine. However, if you think of wireless sensor network we have discussed so far, we have several times said that the type of traffic which is out there in sensor network is of convergecast type, which means that it's traffic coming from the clients, from the sensor nodes up to somewhere in a central kind of point, a sink. Okay, and more than that, especially for environmental monitoring application, this kind of traffic is kind of periodic, which means that the sensor node collects traffic periodically to a sink, which then processes it somehow. Okay? So, on one side, you have an application layer protocol which requires someone to poll every time a sensor node to get out information. On the other side, you have application scenarios where you have nodes which periodically have to send up information. Okay? So if you want to support these second application scenarios using this pull-like transaction approach, you would have to have some clients which poll periodically all the sensor nodes, okay, to get out information. Okay? That's very, I would say, stupid to do, right? Because if you know that the information is to be transferred every second, okay, I would like not to have to poll every second the sensor to get out this information. So I would like the sensor themselves to send me the information without the need to issue confirmable messages with GET requests and so on and so forth. Why not? Because these are overhead. So these confirmable messages for GET requests are overhead. Okay? So the solution is that there is an operation mode of COAP which is called observation, which is an optional one, okay, which actually implements I would say, triggered exchange of information between server and clients. So if you use observation mode in COAP, okay, the servers themselves, they are allowed to send up information to clients, even if they don't have received before a request, a specific request for that information. Okay? Let's see what happens. So suppose that we want to have a periodic reading of a specific resource. For example, we are interested in reading a temperature in a given, at a given sensor with some type of periodic pattern. Okay. Suppose we want to do it with observation. To do that, what we do is just we issue a request message, just like before, for a specific resource, which is temperature, okay, with a specific token, which is such. Okay. But then, different than what we have seen so far, we include in this request one optional part of the header, which is specifying a code which reads observe semicolon register, which means that the client itself is telling the server that is willing to register to receive information on that specific resource, which is temperature in this case, periodically. Okay? So this means that once the server has received this information, okay, it maintains a state on this information, which allows the server to send back response messages, okay, even if they're not stimulated. So for example, it will send up a response message including a content, okay, which is a temperature sample, okay, at some point of time. And then it will send up following response messages at different points of time without the need of receiving before any request from the other direction. Clear? Then, in this observe kind of optional header part, you can specify whether this registration is for a periodic service. So for example, you can say, get me one temperature sample with a frequency of 1 Hertz, so once a second. Okay. Or you can specify whether you're interested in having a temperature sample only when something changes. So only when a given reading is different with respect to the previous one of a given threshold. Okay? This is specifiable within this header here. Okay? And this goes on until the client side unregister to that specific resource. So it needs to tell the server side that it's no longer interested in receiving that specific kind of resources. Okay? Clear? So from a practical point of view, what you save if you use observation mode is basically one request message for all these three, in this case, response messages. Okay, so if you had not used observation mode, the client side should have issued one specific request for all these three response messages. Okay, which you don't have here because you are using observation mode. Clear? Questions? Okay. One last option, which is again very useful, is a so-called COAP block transfer. Again, all these options are being specified because there were some problems with plain implementation of COAP. So let's start with the problem now. I mean, in the previous case, the problem was that the pool-only paradigm was not very, let's say, efficient from the signaling point of view, if you have this periodic kind of traffic pattern. The problem here is that we really want to avoid fragmentation, segmentation, fragmentation at the IP layer. If you remember, one of the two features, one of the two adaptation features of IPv6 LoWPAN was fragmentation. Okay, so it defined a bunch of rules to take one IPv6 packet and chop it off into different fragments. Okay, we have commented though that this fragmentation again as an overhead in terms of a header to be added to each of the fragments and so on and so forth. So to avoid fragmentation, what basically COAP can do is to bring up fragmentation at the application layer. Okay, so to let the original node fragment the information such that fragmentation is no longer needed at the IP layer, at the adaptation layer. Okay, so basically to centralize the fragmentation process at the source of information and not just spread it out through routers, 6LoWPAN routers. Okay, clear? Let's see an example. So suppose that again we want to have a specific resource. We want to read a specific resource, which is a light. Again, we issue, or better, a client issues a confirmable message of request type get light. Okay. And then suppose that this specific resource the client is interested in is a huge one. So it's not just one one light sample, but for example is a kind of log of lumen sample, light samples taken in a time range of 1 day. So suppose that all this information would not fit one single IPv6 packet or one single IPv6 with LoWPAN packet. So what the server side can do is to basically implement fragmentation at the server side, at the application level. Okay. So for example, it can answer with an acknowledgement message, specifying though that the content of this acknowledgement message is just a part of the information which was requested. Okay. So using this optional field, which is called block2, you can tell the client side basically that what is coming after is just a part of the information, and it can specify just like we have seen at the IP layer. Okay. For example, the number of the unique ID of the fragment which is sent back to the client in the specific message, whether there are more fragments to be sent down, and what's the block size, so what's the fragment size. Just like we have seen for plain and classical IP fragmentation. Okay. So basically, the server is sending down one single fragment, then the client side can get to know that the server is fragmenting, which means that it can issue requests for additional blocks. Okay, so it can issue following requests for the additional blocks, which are part of the only single information log which was initially requested by the client. Okay, and all this stuff is done by just including in the message header some optional fields, which is in this case called block2 field. Okay, optional fields. Okay. Questions?
Excuse me.
Yes.
Acknowledgement is inside the confirmation message
Where?
from the client side.
Where? Which one? So you have the first request, which is for the whole thing. Okay. Then the server is telling back, fine, I'm sending you the first chunk of information, but there's more. and this happens with this acknowledgement here, with this header. And then since the client has received the information that there is more information coming, it issues a new request. And then you keep on going like request for a specific block, response for a specific block, and so on and so forth. Did I answer to your question? Other questions? Okay, so let me conclude very briefly talking about discovery and semantics. So what I mean by the discovery? Discovery means that suppose that you switch on your network, let's say from the application point of view, and when you switch on your network, you don't really know which resources are where. So you don't really know what kind of resources are available at one specific sensor node, okay? Whether a sensor node has a light temperature, or light humidity temperature sensors, and so on and so forth, okay? So there is one way, which is a universal way to discover resources at the application layer in the COAP protocol. It's also in HTTP, but let's focus on COAP. And this way is basically defined through a very specific request message. This request message is a multicast message, which means that it's a message which is conveyed in a multicast way downwards, through the IP layer. And the semantics, the format of this message is GET, so it's a request message, okay, for what is called well-known core resources. So this is basically one COAP message which is dedicated and broadcasted to all the nodes in the local network, I would say, to get back information on the type of resources which each node is handling. Okay? Clear? This message here can be, as I was saying, either sent in broadcast, so either piggybacked into a broadcast kind of IP packet, okay, or it can be sent unicast once the network topology has already been discovered. So if all the nodes already know what is the network topology they are in, for example, they know what is the routing tables, they know the routing tables, they know which is the address assigned to all the nodes, then if this is already known, this message here can be conveyed in a unicast kind of IP packet, IPv6 adapted packet, to one specific destination node. Okay. And usually this is the way to go, because if you issue this kind of message in broadcast, you have a lot of congestion, which means that you might have some problems in medium access control. Okay? So usually it's much better to first discover topology, so to first, for example, run RIPL, okay, which means to first get to know who is where from the address point of view, and then issue unicast message, COAP message with this kind of semantics. What you get back out of this message is basically a list of all the resources which are available at one node with a very, very synthetic description of these resources, or better, is a response COAP message whose content is a textual file, text basically, which lists down all the resources available at one node and one very, very simple description of that specific resource. This is all standardized. Okay, for example, if a node has a temperature sample who is allowing to be operated using the observation mode, it will return a line in this file saying /temperature O, which stands for observation mode, and so on and so forth. So all this stuff here is standardized. Okay? Clear? Questions? That's an example. So one guy wants to know what resources are available at the server, so it issues a confirmable message including a request for that specific URI, which is the uniformly recognized URI for getting all the resources. which is slash well-known core. And then what the server answers is basically, again, an acknowledgement message because it was a confirmable one. And the content of this message is the response, including all the resources which are available. Okay. Resources, I mean, this kind of response files have this format, here, okay, which is again a standardized one. Okay, I'm not interested in you to remember what it means, EF, RT, and so on and so forth. It's just telling you what kind of resources are there and what you can do with those resources. Okay, for example, activate or non-activate the observation mode and so on and so forth. Okay? Questions? Okay, so COAP, as I was saying, is kind of well-supported protocol, even if it's kind of new, but it's already well-supported. There are a bunch of implementation of COAP already available, so if you are interested, you can play with some of those. Okay, and as I was saying, also COAP is available in Firefox. So, for example, Firefox is able to issue COAP compliant requests and implement the server side of COAP compliant responses. Okay. Wireshark, for those who know what is Wireshark, as a COAP plugin. You know what Wireshark is, right? Okay, it's kind of a packet sniffer analyzer tool. Okay, it's able to read COAP packets, so it's able to tell you what kind of content of COAP packet is reading in the network interface. Okay, so this is just to say that if you want to know more, to practice more with COAP, there's plenty of, let's say, places where you can find software documentation and so on and so forth. Okay. You have questions on this part? So, just one final remark on where we stand right now. A placeholder for the course. So what we have done was basically to conclude the overview of the two main protocol stacks for wireless sensor networks, which is ZigBee and 6LoWPAN. What we'll have to do in the future is to do some, I would call them spatials, so spatial topics related to sensor networks, and basically we miss 3 of those. The first one will be clustering, which is kind of a side topic which often happens to be seen in the field of sensor networks, which means basically how to decide how to impose some kind of hierarchical structure to sensor networks, which can be useful, for example, to define and design medium access control protocol. The other special topic will be localization, which is kind of hot topic nowadays. So how to localize devices, human beings, objects using sensor network technology. Okay, so we'll have also one specific topic on that. And the last topic will be on RFIDs. So if you remember, at the very beginning of the course, we made the distinction between active sensor networks and passive sensor networks. Up to now, we have focused on active ones, which means battery-operated ones. Okay. In RFIDs, we will see how sensor networks which do not have batteries, okay, are operated. Okay. So that's the plan for the next couple of weeks, I would say. Okay. I'll see you next week, though.